All right.
Is there a reason that S in factor.s is capitalized?
Yes, there's a reason. When the source code, sorry?
I didn't.
When the source code has a lowercase extension, it doesn't go through the CPP, it doesn't go through the C preprocessor. When it starts with an uppercase S, it does go through the preprocessor.
Okay.
And going through the preprocessor is actually important in this case because I'm relying on the preprocessor to generate a dependency file. So we'll kind of go through, well, I don't have to do it today, not in today's class, but eventually I will explain how a makefile works. So in this case, that's going to be important. Okay, so I'll just go ahead and decompress the archive file from my downloads folder. It's called patty. It's called patty because it starts like the patty of a hamburger. It is sandwiched in between two layers. Okay, so the main is going to call your subroutine, which you will have to write in assembly code, and then your assembly code subroutine will have to call another C subroutine. At least you will actually have to call two subroutines written in C. So you have to so that's why you're kind of sandwiched in between two C subroutines. Okay. So after you decompress, you will see a subdirectory called patty, and then inside the folder you'll find all these files. What you are going to implement is not find factor. You'll be implementing factor.c, which is a regular C program. Okay, this is the C version of the program. Factor is a subroutine, is a function that returns a 32-bit unsigned integer. It takes a parameter that is a 32-bit unsigned integer. It has a count local variable. Count goes from 0 to the number of factors in a particular number. As long as n is greater than 1, you will stay in the loop. For each iteration, you will find one particular prime factor of n. You print it out using printf, and then you divide n by f, which is the factor. So n becomes a smaller number. You increment count, and then you go back to the beginning again. All right. Hey, the first thing I want to do is to make this program run so you can see what is the expected output. So you put factor.c into C source, which is a definition of all the C programs, the source code written in C, and then you just take it out of factor.s. You can just use a pound sign to comment out that particular one, and then you run the make program. You say make clean first to make sure that we don't have any left over from a previous attempt to make the executable. And then you just say make. Make by itself will create the executable. It will go through all the compilation, assembly, linking, and whatever is necessary in order to generate the executable, which is just called main. Main as a program, you can just run main, /main, and then give it a number on the command line itself. It parses the command line itself to find out what number it is supposed to factor. So give it a number to factor to break into prime components.
36.
36? Okay, we'll just do 36, just like that. And you can see that it factors 36 to 2 times 2 times 3 times 3. And then it will do the counting too. It says 36 has 4 prime factors. Okay, so that's what the program is supposed to do. And as I said, for those of you who took cisp310 from me, this should look somewhat familiar because we saw this kind of pseudocode already. Are there any questions about the behavior of this program? If you give it like 256, it will just give you 8 2s, because 256 is 2 times 2 times 2, 2 to the power of 8. If you give it a prime number, it will just give you that number back because a prime number has no factor other than itself and 1. So I can just test it again, with this time with 361. Well, that's not a prime number. In fact, it is a square of 19. I did not know that. And how about 3613? That's a prime number. Okay, so 3613 is a prime number, so it doesn't print anything other than itself, and it says it has only one prime factor, which is itself. Are there any questions about the overall behavior of the program? You don't have to do anything about main. Okay? So if you look into main.c, it has the usual main function. It's just a lot of kind of gibberish kind of thing. If you want to read it, that's fine. But you don't have to change anything in main.c. Main.c, the only line that you kind of have to know is this line here. It calls the subroutine that you are going to write, and it has to return a number, so it can store that number in num factors, which is the number of factors. Okay, that's the only line that is related to what you have to do. The rest, if you want to understand how it works, it's good. If you don't have that time, that's okay too. Main does certain types of error checking. If you run main without any parameter, it will tell you that it is expecting at least one argument. If you try to give it something that is not a number, it will complain and say it cannot be interpreted as an unsigned decimal number. So it does some error checking. No big deal. You don't have to worry about any of that. Okay. And then find factor is another subroutine where you don't have to worry about it, but you can also look into it if you're interested. It's really just a very simple subroutine to find a prime factor given a particular number. Nothing fancy, just really simple stuff. There's a loop. It doesn't call any other subroutines, but it does return a value. So your job is to look into factor.c and implement factor in assembly language. But it has to be able to interface with main because it is called by main, but it also has to interface with find factor and printf in this case. Are we doing okay so far with what you have to do? You have 12 days to do it from today, so I think that's plenty of time. So over time, we'll just kind of go over all the necessary concepts that you have to understand in order to get this done. Are we good?
We have to use printf?
Yes. Well, you have to print the number out as in decimal.
Okay.
So if you want to implement your own print decimal subroutine, that's good too.
Okay. Can we change the makefile to do that, or?
I suppose, but you still have to call find factor, because the idea is I have to know that you can interface your assembly code to C subroutines. Printf is not really that hard to use. I mean, you're really just passing the address of the string, and also, in this case, the value of f, which is a local variable. Okay. Are there any questions at this point? Yep.
Do C or C++ programmers ever use assembly, write assembly functions or anything?
Sometimes, if they know ahead of time that writing some code in assembly by hand is going to be far more efficient, yes, they can. But the bottom line is, we want to understand the mechanism behind the scenes, so that when something goes wrong, we can at least try to understand, okay, what can cause a problem like that, and that's partially why we are writing subroutines in assembly, just so that we know what is happening in the background. All right. So with that in mind, we'll go over the first sample program in this class. It has to do with how do we return a single value in a subroutine. Okay. All right. So getting back to here, I'll just go ahead and write a I'll just call it test1, because that's all it's going to do. Test1 itself is written in C, and I'm just going to use a pound include standard io.h, and main does not use any parameter in this case. And all it's going to do is to say printf, and it will print a particular number as an unsigned number. That's what the %u is about. New line character, and the number I'm getting to print out is coming from a subroutine. Okay, so I'll just call this subroutine XYZ. Okay, just like that, and return 0. I need a prototype to define what XYZ is. So XYZ is going to return an integer. I'm not even bothering to use uint or int 32_t. Int itself is a 32-bit integer. So, and here's a prototype. That will make the C compiler happy. Without the prototype, the C compiler will complain and say, I don't know what XYZ is supposed to return, and this will help the C compiler be content about the code here. Okay, and then I'll write XYZ as a separate file. We'll use the uppercase S extension in this case. Other than the extension, the case of the extension, it's really the same thing as what we usually use. So we start with .text because this is actual code. It has to go into the code section. We have to use global XYZ because we need to export the symbol XYZ so the linker can see it. Okay, it's just like .global underscore start was needed because underscore start has to be known to the linker, so the linker can find out okay, what is the entry point of a particular executable. In this case, this is not an entry point, it is really just a label, so the linker knows where XYZ is located. And then after that, we can just say XYZ and a return instruction here. The convention of returning anything that is 32-bit or less is to go through EAX. In other words, if I have a very simple instruction here to put a particular value into EAX, that is what is going to be printed from main. Okay, so it's a very simple test. I just move a particular constant to it. So we'll just go ahead and move something that is unlikely to be, just so happen to be in EAX at a particular time. Okay, so I'm just going to move this constant into EAX and then followed by a return immediately. Are there any questions about this? We actually talked about this on Tuesday already. On Tuesday, I implemented a subroutine. I think was it to add two numbers and return the sum? Yeah. So we already kind of have tested this, but this is really as simple as it gets to illustrate the concept of a return value. As long as it is a simple thing to return, it is just in EAX. All right. So now we have two source files. One is called test1.c and the other one is called xyz.s. Without a makefile, it is you can do it in one single command, which is not really the proper way to do it. The improper way to do it with one single command is gcc-o to specify the name of the executable, is test1, -g to specify to include debug information. And then you just specify the source files. Even though XYZ is in assembly code, GCC from the extension of the file can figure out what to do with it. So this is perfectly okay. Press the enter key, and I forgot it's test1.c. Here we go. And if I run the program, which is test1 in this case, it just prints the number out. Okay, the number was specified as a hexadecimal number in the file, but if you do the conversion by hand, I'm pretty sure this is going to be the actual value in decimal. So are we doing okay so far as returning a number is concerned? Okay. How many people still remember how to pass parameters? Or inside an assembly program, how do we get the parameter?
Stack.
It's from the stack, exactly. So the next program is going to illustrate just that. Okay. So I'm writing all these small, tiny little programs to illustrate one concept at a time. But you have to combine all these concepts, into your own program. So test2.c includes, its own main subroutine, and I'll just include stdio, just for the input-output aspect out of it, of this particular subroutine. Return 0, and then in this case, we'll just do the same thing as last time. Print an unsigned number. I did a prototype here. Unsigned sum xy. So this is pretty much the same thing as what we had earlier in the previous class. Redo. I undid too many times. Just a prototype, and then we have a single printf to print the result of calling sum. So I would just call sum with some kind of random integer, just like that. So are there any questions about the main subroutine itself? Yep.
How does how does the C language understand what you're returning? What if you wanted to return something that was like 64 bits?
If you're returning something that's 64 bits, I have not figured that out yet. But I think a 64-bit result is returned in EDX and EAX. We can test it. Okay, we can easily test it by observing the registers after it returns. But I think that's what it is, how it returns a 64-bit. For those things, for the most part, you can just do experiments to find out, or you can read GCC specification because it probably is documented somewhere in the GCC documentation. All right, so this is the subroutine that I'm testing, which is sum. Now I have to write sum in assembly, okay, just like I did it with XYZ earlier. Same thing, we have to start with .text, and then we say global, in this case, sum, and then we write the subroutine sum. Okay, now before we go any further, I always prefer to use symbolic names to get to the parameters, just because it is easier for me to see how the stack is laid out, how different items on the stack are laid out that way. So we'll say the return address equals to 0 because the stack pointer points to the return address at that point. When I'm in the subroutine. Now, if return address has an offset of 0 from the stack pointer, where would be the first parameter?
32 bits later.
Yep, it will be at 4 locations higher than return address because return address itself takes up 4 bytes. So this will be return address plus 4. And y is the second parameter. It will be at the location where x was, but you have to add the size of x to it too. So this will be the way I calculate the offset from the stack pointer to a particular item on the stack. Okay. Now obviously, if you look at the math here, you can just say x equals 4 and y equals 8. But I prefer it like this because it really shows the relationship between the items on the stack. So in case I want to insert a new parameter in between x and y, I can adjust the equations. And later on, it will become more useful because we'll also use this method to access local variables. So inside the subroutine, I can do the calculation. I have to move one of these into a register. Now since I need EAX to return the result anyway, I'm going to copy one of them into register EAX first. So the way to do this is to use the based addressing mode. So x open paren %ESP close paren is basically saying go to where ESP is pointing to, but not exactly that location. Add the constant x to that address, and that becomes the effective address. What is at that location? ESP points to the very last thing that was pushed on the stack, which is the return address. The parameter x was the second last item pushed on the stack, and that's why it is right there. Okay, it is right at that location. And then the next instruction is add L, Y, ESP, EAX to access parameter Y, and we are adding that to EAX. EAX by convention is used to return the value anyway, and now I have the value already calculated. It's in EAX. I'm ready to return. Are there any questions at this point about how this works? No questions or not?
Kind of the return address is put on the stack first.
It's last. So when you call a subroutine, from the caller's perspective, it will push the last parameter, then it will push the second last parameter, and so on. So it works its way backwards on the list of parameters. the first parameter is pushed last. And then it will do the call. So the call instruction is really the last push because it has to push the return address. This is from the perspective of the subroutine call, and then later on we'll also look at it from the perspective of the caller and see how we can set up everything in assembly as well.
But if the last thing on the stack is X, right?
Okay.
And
So if you look at how memory is laid out, I'm gonna use a text editor or maybe a spreadsheet. A spreadsheet is even better because it's already a table. Okay, so if you use a spreadsheet to represent the items on the stack, I'm just debating whether to replicate the subroutine here. I'm not going to replicate the subroutine. So what I'll do is I'm just going to kind of display the items on the stack in this particular case. So Y is going to be at the highest address because it was pushed first. X is pushed next, so it has the lower address. And then the last one is the return address because the call is the third instruction or the third thing that you're pushing on the stack. When you read this, everything that's higher up has a higher address, everything that's lower has a lower address. And this is how the stack is laid out. By the time I get control in sum, this is what it looks like. Now ESP, the stack pointer, always points to the very last item. So that's why ESP is always pointing to, in this case, is pointing to the return address because the call instruction was the last thing that pushed something on the stack. Is that okay so far? So even though in here, X seems to be just one item away from where ESP points to, but one item, in this case, the return address, has 4 bytes. So that's why when you are calculating the actual address of X, it is 4 bytes after where ESP points to.
I have another question.
Go ahead.
That, how come is in C++, or I'm guessing this works this way in C too, when you have multiple parameters in a function, how come that when you use like the increment operator, it's not really defined on which one it goes off first? Like if you have like 3 integers and you use like plus plus x plus plus y plus plus z, apparently it doesn't. There's no order in which those, like no particular order in which they are done first.
It is not specified by the language. I think when you have those 3 as parameters, it doesn't say which one is done first.
Yeah, why is that?
It's just not specified by the language. So it's implementation dependent. And that's why for something like that, you should not make your program sensitive to the ordering of evaluation on the list of arguments. Because you can run into problems where the order of evaluation can make a difference. Most of the time it does not, but sometimes it can. It depends on whether the operation itself has any side effect. Right. So are we still doing okay so far with this code here? Okay. So the next thing we'll do is we'll just go ahead and assemble and test this code. So we have test2 in this case, and then sum.uppercase s. And this time I'll use GDB. I'll use GDB to actually stop in the subroutine itself so we can examine the content on the stack to confirm our observation. This is something that we did on Tuesday as well. So we'll put a breakpoint. When you set a breakpoint, you can put it on a particular line. You can also use a label. So in this case, we can say break at the entry point of the sum subroutine, and that will do it. You run the program. Now we are at the sum subroutine. This is before the first instruction executes. Just like last time, I'm going to display 3 items on the stack, each item being a word, which means it's 32-bit, and it is printed in hexadecimal. And we'll start with wherever the stack pointer points to. So those are the 3 items on the stack. The leftmost one has the lowest address, which is the convention of printing content from memory. That's our return address. Okay, the 0A048439 is actually a return address. And then the next two, the other two items are the actual parameters. 3/8 in hexadecimal is 3 times 16, which is 48, plus 8, which is 56. That really is our parameter x. The second one, 3E8 is 1000, written in hexadecimal. Okay, so those are the items on the stack. Now, when I single step this instruction on line 7, moving the base operand into EAX, I can look into EAX and make sure that it does get the right value in the register EAX. And then if I single step the second instruction, it should add 1000 to EAX. And here, I just confirm that it is actually adding the right number. Now, at this point, I can continue execution at full speed, and the program should print 1056 to the screen because of the printf statement, and that's exactly what it did. Do we have any questions about this part? No questions? Okay, so the next thing we want to do is to say, okay, now that we know how the stack is laid out in terms of parameters by the time we get to a subroutine, how do we set that up in order to call a C subroutine from assembly? So that's the, I'm just looking at it from the other perspective, from the caller's perspective instead of the callee perspective.
Push the last parameter first.
Yep, pretty much. So what we'll do, I'm just going to use test 2 as a baseline. I'm going to change it to test 3. So in test 3.c, what I'll do is instead of calling sum as a subroutine, in fact, what I'll do is I will implement sum in C. Okay. But instead of calling sum here, I'm going to call another subroutine. I'll just call it G. Okay. I will use this mechanism to basically mean that whatever code is between #if0 and #endif, that will not be compiled by the compiler because the preprocessor will basically just ignore everything in between. So G, which is a subroutine that I am going to implement, is going to be implemented exactly this. It will just simply return some, and then we'll use some 34 and 400. Okay. So this is what I want to implement. I'm going to implement G in assembly, and then the rest will be implemented in C. So this is kind of like your PADI homework assignment, except this is a lot simpler, because G is sandwiched between the main subroutine and also the sum function. Are there any questions about how this is set up and what I'm actually trying to accomplish? No questions? Okay. All right. So what we'll do is we'll yank 4 lines here, and then start on the subroutine called G. And I'm implementing one subroutine. Oh, I guess it didn't copy the whole thing. Now, when you are using the uppercase extension, you have to be careful because if you have pound and then an if somewhere, the preprocessor will catch it. It's not really considered comments anymore because pound if is a correct preprocessor directive. So in that case, you have to say pound or pound space pound, just so that the preprocessor can properly ignore that. But in this case, we are not running into that problem, so we don't have an issue. So once again, dot text to switch to the text section. I think that's the default to begin with, but it doesn't hurt to double check and make sure. Dot global G in this case, because G is the entry point of the subroutine, I have to export it. And then we have a G colon to start the subroutine and then return at the end of the subroutine. And this is the way I usually write my subroutine. I really don't care what is in between. I always start with the label and also make sure there's a return statement or return instruction at the very end, just in case I forget to put that return instruction at the very end. Because forgetting to put that return instruction at the end is very bad. Because what happens is, it depends on the link order. The execution would get past the last instruction specified in this file and move on and continue on the first instruction of whatever the next object file is. So the result of that whole thing can be very confusing because I'm calling G, but it's going to be returning from the next subroutine. And obviously the stack is not properly set up for the other subroutine. So things will just kind of go crazy and difficult to debug. This doesn't take much time. Just put it there to begin with, and not having to worry about that later. Okay. So now the question is, how do I invoke or how do I call the sum function setting up these parameters? The way to do it is to push the last parameter first because it has to be the one with a higher address. So 400 in this case is pushed first, and then 34 is pushed second, and then you just call the subroutine. And that's all that I have to do in this case because sum is going to return the result in EAX, and I'm supposed to return my own result in EAX as well. Well, since it's already in EAX, I don't have to move anything in this case. Is that making any sense so far? All right. Well, let's go ahead and make sure that this does work the way it's supposed to by testing it. So dash G dash O. Let's see. G dot uppercase S. And I'm just going to run this whole thing. Ooh, okay, it doesn't work the way it's supposed to. Can anyone guess why? It is not intentional, but it's nonetheless a very good demonstration of what happens when the stack is not balanced. Okay, by the time I get to the return statement, what is the stack pointer pointing at that point? What was the last thing that was pushed?
The address.
No.
34. Oh, something.
Yes, the constant 34. The constant 34 was the very last thing on the stack by the time I get to the return statement. So it will use 34 as the location to return to. Okay. Now when you run this without GDB, it doesn't give you a single clue of what is happening. Okay. I can already pinpoint where it is because I've done this many times. But if you run it in GDB, it does give you a clue. So let's go ahead and run it in GDB with the same mistake. This is actually good. This is turning out to be better than planned because I just accidentally introduced a bug into this program. Okay, so I'm going to run this full speed in GDB, and you can see that in GDB it gives me a segmentation fault, which doesn't seem to be very helpful. But look at the next line. The last line of the output says it's at the location 0, 0, 0, 0, and then 2, 2. What do you think is the value of 2, 2 in hexadecimal? 34. Turns out to be exactly 34. So why would I try to execute some code at location 34? And 34 turns out to be one of the numbers that I push on the stack. Isn't that kind of, do you think that's going to be helpful? When you just look at the location where the problem is occurring, that would sometimes give you a clue already. And this can happen in C2. If you corrupt the return address, this will tell you, what can potentially be causing that corruption. Are we doing okay so far? Okay. So next, we have to fix this problem, right? We don't want to continue execution at location 22. So the question now is, how do I fix this particular problem? In other words, I want the stack to be balanced again. So I have to do something here. Whatever I push, I really should pop, or I should reclaim that space on the stack. In this case, I can use pop into, say, EBX or some other register, but I really have no use of the constants 434 anymore. So what is the quickest way to reclaim that space without having to store that somewhere else? Just move the stack pointer, okay? So in this case, I can use the add L instruction to change the stack pointer. So I'll give this one to you as a little exercise. What should I put here? 8, exactly. Okay, because I allocated 8 bytes from the 2 push L instructions. Now I'm just going to get rid of those 8 bytes by moving the stack pointer up by 8 bytes again. So I'm not actually moving anything except changing the stack pointer itself.
Is it like bad form to leave random stuff in the stack that you don't need anymore, or you're supposed to clean it up?
Well, if I don't clean it up, I cannot execute a return
Oh, no,
statement.
I mean, but right now you're not really cleaning it up. You're just moving the pointer. The stuff.
But it
still
is
there.
cleaning up. Because
Okay.
remember what the stack pointer is? The stack
Yeah.
pointer is really a bookmark
Yeah.
that separates the stack into quote unquote two portions.
Yeah, but instead of doing this, you would pop.
Right, but pop is unnecessarily wasting memory cycles. The compiler would do this too. I mean, this is a much faster
The
operation.
compiler would optimize out the pops and do it.
Well, the compiler will think, there's no place to pop it into. Nothing really needs the 400 and the 34 anymore. So it will just do whatever is minimum in order to adjust the stack pointer back to where it's supposed to be.
The reason we don't pop to some random place is because whenever you push something back onto the stack, that spot's just going to be overwritten again anyway. So you don't need to clean it up. Popping things
Right.
onto the stack take care of the cleaning up itself.
Yep. So this is, a proper way to clean it up. Yep. All right. Well, I claim that this is the fix. Let's check and whether it's, to see whether it really is going to fix the problem or not.
Didn't you say we can't modify the stack pointer directly?
Sorry?
We can't modify the stack pointer directly?
Say again?
I thought we cannot modify the stack pointer directly.
Yeah, you can. It's the instruction pointer that you cannot modify directly. EIP you cannot modify directly, but ESP, the stack pointer, yes, you can. All right, so we'll go ahead and test the program again, and this time it doesn't have a problem, okay? Because we adjusted the stack pointer back to where it's supposed to. Yep.
Oh, right.
Didn't
It's not
we
gonna work.
push the wrong parameters on the stack, like in backwards order?
No, we pushed it in the right order. 400 should be pushed first because it's the second parameter.
You say?
You push the second parameter first and then the first parameter.
But isn't the return address under?
I suspect.
The return address is the last thing on the stack because the call follows the push down instructions.
How big is the 64-bit address?
Remember the stack's upside down too.
Yeah. We usually look at the stack kind of upside down. It has to do with. Okay, see the first instruction is a push L 400. So 400, or the 4 bytes that is representing 400 is going to have a higher location because the stack pointer goes lower as you push items.
Okay, sorry.
Right? So that's why the 400 has the highest location, 34 has the next 4 locations, and then the return address coming from the call is going to have the lowest 4 locations.
No, I mean, like when you call sum,
Right.
it's going to put 34 as the first, and then 400 as the next. So,
Right.
So does sum pop push the 34 and the 400, or is it just like,
It's the same way that we implemented sum. So if I look at, okay, we'll do this. So on one hand, we'll look at G, and then the other hand, we'll look at sum here. Okay. So when in sum,
oh wait,
sum
are we calling it assembly sum?
no, but it's going to work basically the same way. The C code will do exactly the same thing, except it's going to do it in possibly different instructions, but it's still using the same convention of where to look for the parameters. So it still has to understand exactly the same standard because even though inside the subroutine it can be using completely different instructions, but as far as interfacing with the caller and the callee, it still has to follow exactly the same rules.
So if sum had 3 parameters instead of 2, would that still work? Would it just read garbage as the third parameter?
Right. If sum is expecting 3 parameters and you are only passing 2, then the third parameter is quote unquote an if. It's some other item on the stack that is not really the third parameter. Exactly. So that's exactly how the subroutine being called will treat the parameters.
How come that's a compiler error?
Because when you write it in assembly, it doesn't know how many parameters are expected. All right. So are we still doing okay? Yep, go ahead.
I know this is off topic a little bit, but on a 64-bit,
Mm-hmm.
how would that add-l command
Q.
work?
Q, yep,
Add
that
Q,
quad word.
16 and RSP, that it gives me like some giant billion number, like 321 billion.
It might be something earlier in the process.
It can be the convention is different too. Yep. Because in 64-bit mode, your integers, if you just say int, may not be 32-bit, it may be a 64-bit already. So the convention may be different. So you kind of have to go through some checks to make sure that your so-called int is actually 32-bit and not 64 to begin with. All right. So we have taken care of a few pieces of items already. The next item is how do we use printf from inside a assembly subroutine. Okay, so that's the next thing we want to do. And this one I can just write it in completely in assembly. Okay, there's no need to write it in C code. Actually, I do. I can implement the whole thing in assembly, including main itself. Okay. So .text, .global. In this case, main is the only entry point that I need in this case. And then we'll just start with main and put a return here. I want main to return 0, so I'm going to put 0 into EAX before the return instruction. Now I can go ahead and try to print something. Let's try to implement this. Okay, so we are trying to implement printf %x, which is printing in hexadecimal, a line feed character, and then we're just printing 1, 2, 3, 4, 5 as a decimal number. In other words, we are printing the hexadecimal version of 1, 2, 3, 4, 5 in decimal. Okay, that's all that this is all that I'm trying to do. All right, so how am I going to do this? Well, it's the same thing. We're calling a subroutine that has multiple parameters. Push the last parameter first, and then you move your way backwards to the first parameter. Okay, the last parameter is easy. It's just a constant, right? So to push a constant, we can just use push $L$ using the immediate operand 1, 2, 3, 4, 5, and that should take care of the second parameter. The first parameter is a little bit harder to deal with because I cannot just say push L, double quote and something. So this is where one of the earlier concepts that we talked about in this class is going to come in handy. We have to give it a label first, so we'll just call it FMT string for format string.
We're going to use string Z.
It's .ASCII, which automatically has a no terminator at the end. So with this, I can just do exactly the same thing here. I'm not 100% sure it will take \n and interpret it as the line feed character. So we'll just give it a try and see whether it works or not. FMT string is our second item, and once again we have to remember to adjust the stack. I have to do the call first. Call printf. And then we have to adjust the stack pointer again by 8 this time, because the address is also a 4-byte kind of thing. So that should do it. All right. So are we okay, or do you guys have any questions about the code on the screen at this point? We are doing the same thing. Push the last parameter first and move our way back to the first parameter. Call the subroutine, adjust the stack pointer to reclaim the space used up by the parameters, and then in this case, because main is supposed to return 0, move a 0 into EAX as our return value, and then actually execute the return statement.
Are we calling the built-in printf from C?
Printf belongs to a standard library. In other words, when you use GCC to compile and link main.s in this case, it automatically knows it will try to link it with the internal libraries, and that's why it's kind of handy. All right, so let's give it a try and see whether it is doing, what we think it should be doing.
Refer to a different header file.
Sorry?
If you needed to return or refer to a different header file, how would you do
The
that?
header file has nothing to do with the linker. The header file is really just defining the prototype so that the compiler can cross-check and make sure that you are in fact using the subroutine as it is intended. The number of parameters, the types of the parameters, and so on and so forth. Okay, but the header file has nothing to do with what library it should be linking with, because that really is the linker's job and not the compiler's job. GCC as a command can do both. Okay, it can be the compiler and also the linker at the same time. But printf is a standard function, and that's why you don't have to supply an additional option to GCC so that it will link with it.
So the same thing would apply, for instance, if you're trying to call square root, which is in the
No, square
math.
root is in the math library, and
Right.
depending on how GCC is set up, I think in some cases you have to use a dash lowercase lm to link with the math library.
So there's a different switch for every library we can possibly.
Yeah, there are different switches, like cursors, the library that you need to place, the cursor somewhere on the text screen, you have to do a dash L n cursors to make sure that it will link with the n cursors library.
And this supports custom libraries too. You just do.
If you supply your own library, then you have to supply the full path to the library file itself, because internal to GCC is a default list of path where it will look for libraries.
Yeah.
Mm-hmm.
Can you modify that file? Can you modify that file?
You can use an option to change that path.
Can you permanently modify that file? Say I have a library that I use a lot. It's my own library.
Yeah, and you want to add.
That's why a make file comes in handy, because you can just define a option in your own make file.
Okay.
Then you don't have to worry about that anymore.
There's no config path file.
For the entire GCC, I do not think so. There
Okay.
may be one, but I am not aware of it.
Okay.
Yep. So -G -O main dot uppercase S. Okay, so this time, the compiling or the assembling of the source file and the linking of the object file is kind of combined into one single command line. And then /main, it prints 30 or 39. So it works the way it's supposed to. Because this is actually in hexadecimal, hexadecimal 3039 is 1, 2, 3, 4, 5 in decimal. Can you guys do a cross check real quick and make sure this is actually the kind of in the right range of value? What is 1000 in hexadecimal?
Yeah. Maybe it's.
Well, it's 2 to the power of 12. 1000 in hexadecimal is 2 to the power of 12. Let's do this real quick.
16 to the power of 4.
Okay, this is in hexadecimal, right? So every digit in hexadecimal is 4 bits. So that's why you have 12 zeros in this case when you look at this number as a binary number.
It doesn't have to be
Right?
65.
So this is basically 2 to the power of 12, which is 4096. Now, since we have 3 of those according to this number, so it is close to 12,000. So it's pretty close to 1, 2, 3, 4, 5 already. So just by a sanity check like this, I kind of know that number has to be right. It's just a quick check, without actually looking at every single digit. I can look at the approximate value of that number in hexadecimal and kind of check whether it is see if it is even close to 12,000. Okay, so we got the printf out of the way. So the next question is, how do we deal with local variables? Well, then you have to ask that question of, is the local variable local to the caller, or is it local to the subroutine being called? That's the first question. What do you guys think? Is the caller aware of the number and the size of local variables of a subroutine? No. Okay. So that means the allocation of local variables is not the job of the caller. Is that making any sense? Instead, it is the job of the subroutine being called. Okay, so that's the first thing that we have to understand is it doesn't change the use of local variables, does not change the caller. The caller is done, okay? We have talked about everything that the caller needs to know. So now we have to kind of focus on the callee or the subroutine being called and say, okay, so how do we allocate local variables? Before we go any further, let me go to sum.uppercase S here. Now sum is a really simple subroutine, okay? But what if I have some additional push L instruction here? Do you think the base operands are still correct in this case? If I have some random push and pop instructions before the move L instruction, that will change the stack pointer itself. Now if I change the stack pointer, it will also change the offset from where the stack pointer points to the parameters. In other words, this approach is sensitive to additional push and pop instructions, inside the subroutine, because any push, any pop instruction will change the stack pointer itself. Okay, and that's not good. Okay, it is not good because a lot of times when we write code in assembly, we used to put the push and the pop instruction to save registers, to restore registers, and do all kinds of stuff that is handy. But that would affect how we calculate the displacement to a parameter. Okay, so that is the reason why we have a frame pointer. So let me go back to my notes here so that you know where we are at in the notes. Because the introduction of the frame pointer is a little bit, it's convenient. It is something that is nice in the end, but the introduction to that can be a little bit confusing. So we are basically at this point, we're at this point here, 13.2, which talks about what we call as the frame pointer. Okay. So what we'll do is I will just go ahead and write the code using the frame pointer first, and then I will go back and explain what it is doing and how it can accomplish what we want it to accomplish. Okay. And we'll go back to this particular example here, and this time I'm changing the offset a little bit. And I would just say, old EBP is going to be 0. Return address is old EBP plus 4. And then X is old EBP plus 4. The rest I don't have to change because they're all relative. And the entry point is now changed a little bit. The first thing, the very, very first thing we do when we get into a subroutine is blindly do a push EBP. And then before we do the return, we just blindly push a pop EBP. Okay, EBP is our frame pointer. Yep.
Is your return address and X supposed to equal the same value?
The return address?
Yeah. And X, they both equal the same value?
No, because this time they're relative to the frame pointer, not to the stack pointer anymore. Okay. So the next, so I need one more instruction. Right after we push EBP, we'll do a move L ESP to EBP. It's basically the same thing as taking a snapshot of the stack pointer and call it the frame pointer at this point. And then at the very end, we do exactly the reverse. We move the stack pointer, the frame pointer back into the stack pointer before we do the pop. So you can definitely see some symmetry here. Let me turn on the line number so we can point out various parts of this code. You can see there's a symmetry. The symmetry is lines 8 and 9 are symmetric to lines 12 and 13 in an opposite order. Okay? EBP is what we call the frame pointer. So inside this subroutine, now that we're using a frame pointer as a reference point, we do not use the stack pointer explicitly anymore. So everything that we want to access, from the stack, we use the frame pointer, or EBP in this case. Okay? Yep, go ahead.
Can you explain again why 4 and 5 are the same? Lines 4 and 5?
4 and 5. Oh, you're right. I got it wrong. That's actually relative to return address. So you guys were right. I got it messed up. Okay. Because they're all one stacked up on top of each other. Okay. But first of all, let's look at those label definitions from line 3 to line 6 and see whether they still make sense or not. And I'll just draw it on the whiteboard here. Y is pushed by the caller. Okay, that's the very first thing that is pushed on the stack. When we have to invoke the subroutine sub. Okay, is that making sense? And then we push X. This is also done by the caller. And then we have a call, which means the return address is pushed next. This is also done by the caller. When we get into the subroutine, we will also push EBP on the stack. This is the old EBP before we change it. Okay. So right at this point, which is on line 8, we have the stack pointer ESP pointing to a copy of EBP. EBP at this point can be pointing somewhere else. Okay? I don't really know or care what EBP itself is pointing at this point. I'm just interested in saving it before I modify it. Are we doing okay so far? Now, when I execute line 9, which is the move instruction, EBP is no longer going to be pointing there. It will be pointing to its own old value when I execute line 9 in the code. Are we still doing okay so far? Because on line 9, I'm effectively making EBP a copy of the stack pointer. Is that okay so far? Now, let's go ahead and think and imagine that this is a really complicated subroutine, and inside the subroutine I have to do all sorts of other things like push L, blah blah blah, and then push L, pop L, and so on and so forth. So I'll just actually get a particular push instruction here, just so that we mess up the stack pointer. Would that invalidate line 11? In other words, the push instruction would definitely put something on the stack. The stack pointer will modify accordingly. Okay, in this case, when I execute line 10, I will end up with a constant of 12 here, and then the stack pointer will point to the 12 instead of the old value of EBP, right? But does that make line 11 the reference to my parameter? Would that make that instruction incorrect? And why do you think line 11 is still okay? It is still accessing parameter X correctly.
It's basing everything off of EBP, not
Because it's going off of EBP. It's not using ESP anymore. As long as I'm not modifying EBP, I can do all sorts of stuff on the stack and not have any impact to the access of my parameters.
You also don't need to balance the stack at this point. You could push 100 things onto it and never have to worry about it popping.
Exactly, exactly. In fact, this program will work just fine because even though I'm not balancing the push on line 10, by the time I get to line 13, what do you think line 13 is going to do? Line 13 will copy EBP back to ESP. So ESP will just go back to, pointing to where it used to point to. And then after line 13, I have a pop L EBP. So that means ESP itself will go back and point to the return address. EBP is going to point to whatever it was pointed at before. So everything is now restored back to the entry point condition. And the next instruction is the return instruction, which will use the correct bytes, the 4 bytes, to return to the call. Are there any questions about how the stack is now set up now that we have the frame pointer concept? No questions? Okay. Now, if we use this particular scheme consistently for all the subroutines and for all the functions, do you think that EBP or the frame pointer can serve a kind of important role in debugging your program? Go ahead.
So pop EBP restores where it points to.
Right.
Okay.
Yeah, because this is the old value of EBP before I modify it on line 9. Okay, so by restoring that, it will just go back to point to wherever it was pointing at.
So is EBP used in like multiple places on the stack?
Well, every subroutine will use EBP. Now, according to the convention, okay, using this convention, if every subroutine is using this particular convention, EBP is now becoming the first pointer to a linked list. Because it points to its own old value, and then that old value points to its older value, and that older value points to its older value, and it just keeps going like that. And this is how GDB can actually, when you call main, okay, main calls F calls G calls H. Okay, by the time you get to H, GDB can backtrack EBP and use it as a linked list to figure out what the other subroutines use the stack, including the parameters as well as the local variables. So that's why EBP serves two important roles. The first one is with the use of EBP, I can mess up the stack, and it doesn't affect how I refer to the parameters. But the more important reason why EBP is also useful is it allows me to backtrack on the trace, on the stack trace, so I can actually see how I got to subroutine H. I can actually see that H is called by G is called by F is called by main, and not only I can trace, how it got there, I can also trace the parameters and the local variables along the way. So it's very, very useful for that purpose. But if you mess it up, then it's really bad because now you lose the ability to backtrace, the entire stack. Yep.
Or in this case, wouldn't 12 be popped into EBP when you're done?
No, it would not, because I have moved EBP to ESP first. Okay, let's reproduce the scenarios. All right, so we'll start with line 8, okay? So on line 8, I'm pushing EBP on the stack. The stack pointer will point here. EBP itself is pointing to somewhere else. So in other words, these 4 bytes is pointing to some other place. Okay, that's the condition after line 8. On line 9, I'm destroying the register EBP, but the saved version of EBP is still on the stack already. So that one is not going to be destroyed. So at line 9, EBP itself will point to its own old value, but as a register, it is no longer pointing to some other place. On line 10, I push 12 on the stack. So 12 as a constant using 4 bytes will be pushed on the stack. As a result of this, ESP will also be pointing to the new value that I'm pushing on the stack. So that's the condition after we execute line 10. Is that making sense so far? I'm just tracing the activities related to the stack as we go through this program. Line 11 and line 12 do not modify the stack at all, so I'm not going to trace it in this in this particular scenario. Line 13 is going to copy EBP back to ESP. EBP is pointing here, ESP is pointing here, but I'm changing ESP so it points back to the same location as EBP. So that's what saved me. Okay. In other words, I cleaned up the stack with one single instruction. Just by copying EBP to ESP, I cleaned up everything that I might have allocated up to that point. So that's really handy because now on line 14, I pop EBP, which is copying the 4 bytes at this location back into the register EBP. So what that will do is it will make EBP also point to the very same location that this thing is pointing at, but at the same time ESP will point back to the return address.
Would it be possible to, instead of move L EBP to ESP, could you move L EBP plus 4 to ESP?
You can do the math. You can actually figure out that, I have 4 bytes to adjust and do the adjustment. But this method is even better because there's no calculation involved. You can have like 20 pushes after this, 25 pushes after this. It doesn't matter at all. Yep.
So 12 would still be on the stack.
Well, because it is below where ESP is pointing at, we can no longer count on these things, remaining the way they are, as they're on the stack. So even though, yes, right after the pop instruction, they are still on the stack, but you can have interrupts and signals and other stuff coming in, that can modify, the stack pointer or the portion of the stack that is lower than where the stack pointer is pointing at. So you cannot really count on these things still on the stack for those reasons. Any other questions? No questions? Okay, so now we want to worry about local variables. Where do we put local variables? Okay, when you look at the stack, we have parameters. We have a whole bunch of parameters. This is the last one. We'll just call it param n. This is our first parameter. We'll just call it param 1. After we push all the parameters, we have a call. The call is going to push a return address on the stack. The old EBP is always here. Push L EBP is always the first instruction inside the subroutine by convention. So this is always old EBP. Old EBP. And EBP itself is always pointing to its former value. Okay, this is a convention. Okay, it's just a convention. When you write code in assembly, you don't have to play by the same rules. You just have to make sure that you know that other subroutines play by these rules. So in this picture here, where do you think would be a good place to put my local variables? How about right here? My local variables can go here. In other words, if I allocate this space for my local variables, I have to move my stack pointer to at least down to this point, if not any lower. Okay? And that's exactly how a C compiler would do it. Okay? It would assume the parameters to be here on the top, then we have a return address, and then we have the old value of EBP before EBP is modified to point to its own former value. And then we have a whole bunch of local variables. Now within the local variables, the ordering should not be important, but usually the last one is here, and then the first variable is usually here. But that's not, that should not be important. Are we doing okay so far with these concepts? Questions? If there are no questions, I will go ahead and give myself another test. Okay? So this time I'm going to write a subroutine in C first. Oh, okay, this one is already, use a different name, main1.uppercase. So I'll write this in C code first, and then I'll translate that into assembly code.
Is this why multi-threaded applications, the separate threads get separate stacks?
Yes. Each thread has its own stack.
So it doesn't corrupt the other threads?
Correct, because each thread can have its own function calls, and that is completely independent to all the other threads. Right, so I'll go ahead and write this particular C subroutine. I'm just going to write it in C first, and I'll comment it out. Okay, int I, and I will just say I gets 0, while I is less than 3. Do the following. Printf. This time it's a %d for signed integers. \n. And then we print I just like that. Plus I return 0. Okay, just from reading the high-level code, what do you think this program is going to do? It'll print some values. Which 3 values is it going to print? 0, 1, 2, because by the time it gets to 3, it has to get out of the loop. Okay, that's exactly what it is supposed to do. Okay, cool. And now we want to implement this in assembly. All right. Text dot global main to export the label main. And as soon as I do that, I put a return here, just so that I know I don't miss that last instruction, which is important. This is really just an entry point, a label. All right. So the most important part about this program is how am I getting those parameters and the local variables? I have no local variables, so old EBP is always 0. Okay, that part is always there. I do not have any parameters, but I'm going to allocate something for local variable I. So what do you think, how should I allocate space for I? In other words, how can I express the displacement to the first byte of I from where EBP points to?
Old EBP plus 1.
Opposite direction.
I'm sorry,
Because old EBP is pointing here, my local variable I is going to be here. So that's why it is actually old. It's actually old EBP, which is an offset. It has to subtract 4 from it because it is 4 bytes below. This is old EBP, right? Okay. So that's how I will do the allocation symbolically. Old EBP minus 4. If I have additional local variables, I would just keep doing this. J is I minus 4, and so on and so forth. And this is just my convention, but I always put a label here as my last local variable. So in this case, I is the only local variable, so I just use I as my last local variable too. Inside the subroutine, okay, the first thing I do, this is by convention, is to do a push EBP. Now, the way I write this kind of program is, it's kind of awkward, because I would do a push and then immediately close it, quote unquote, close it with a pop. Because this way I don't forget. I know exactly where it's supposed to go, and I don't forget actually doing it. If I miss both at the same time, it's not as bad as a problem as if I just miss the pop. Okay, missing the pop is really, really bad. Okay, and then the next instruction, by convention, is always a move L ESP to EBP, and then to match that, the second last instruction before the return instruction is going to do exactly the opposite, to restore the stack pointer to where it's supposed to. Okay, so once again, it looks like it's a waste of time by moving back and forth the cursor, but this way I know that I won't forget to close whatever I did earlier. Now I can allocate for the space for the local variable. It's just add L $last var to the stack pointer. I'm not even pushing anything because it's a local variable, it's not initialized. So all I really want to do is to move the stack pointer down to allocate that space, and it becomes an uninitialized local variable. Are we doing okay so far? The add L instruction works because the value itself is negative. So it is really the same thing as subtracting a positive quantity from the stack pointer. Okay. Now this guy here, okay, if I turn on line numbers, line 12 doesn't have a match at the end because that one single instruction on line 21 is going to fix everything. So I don't really need to subtract last var from ESP, right before the last few instructions, because it is going to balance it correctly anyway. Okay. What do I do with this initialization of my local variable I? Move L $0 because it's just a constant on the right-hand side of the assignment. How do I move this into my local variable I? It's just that. Because the symbol I is not the actual variable I, it is the displacement or the offset to the local variable I from where EBB points to. So using the based addressing mode, I can now get back to the local variable. In other words, as far as addressing mode and the way we access these items is concerned, there's no differentiation between a parameter versus a local variable. It's just that the parameters are on the positive side of ODBP. Local variables are on the negative side of ODBP. That's the only difference, but as far as addressing modes are concerned, it doesn't make any difference.
So here you're just using the stack to access variables rather than registers.
Correct. Well, local variables are always on the stack, unless you specify it to be static. When you have a static local variable, it is actually the quote-unquote in the global space. It's always there. It's very rare that you need a static local variable. It's usually a bad idea to do it that way. Okay. So now I can try to finish the rest of the code. Yeah, I think that we got enough time to do it. Okay, so the next one is a compare long to 3. Okay, with I percent EBP. If it is not less than, in this case I have the JNL because it's a signed integer. So JNL to end while, and end while goes here. Return 0 is move L 0 into EAX.
Need a colon after end while.
Oh, that's right. And because this is a loop, I also have an unconditional branch back to the beginning of the while loop. And the beginning of the while loop has to be before the comparison. So begin while goes here. And now I can implement the printf statement. So once again, I have to push the last parameter first. The last parameter is my local variable I. This is how I can access the value of the local variable I. And then I have to push the format string, $format string. And just like last time, we can define the format string up here. Anywhere before the main label is fine, we can put it here. So format string is the address of .askeys, which has a null terminator at the end, %d \n. after I push the parameters, I can actually do the function call, call printf. Now, in this case, I really don't need to reclaim all that space. In other words, I can keep chewing up more space on the stack because the move out instruction at the end on line 33 will clean up the stack anyway. But if I don't do this, add L %8, ESP, if this loop has to go through a lot of iterations, it will eventually chew up a lot of space on the stack, and you can run out of stack space because of that. So just for being correct, I should do that.
Is there a way to control how large the stack is?
I think that's deep inside the kernel, or maybe it's controlled by one of the /proc or probably one of the /proc variables can control that. All right, so adding one to I is just like that. I think we're done. Let's give it a try. gcc-g-o main1 dot case test. Wow, it actually assembled the first time. And run the first time. Wow. But are there any questions? You really have everything that you need to know to do your homework, at least to get started. Okay, but don't just sit down and start coding. Make sure you understand the concepts first, okay? Because that really is the most important part. Any questions? I think I should upload, all this code to Moodle, and I found a really good, easy way to do it. I know most you guys are not really excited about this kind of thing. It's Ajax, so I can turn editing on, and then go to a file manager. To go to today's folder, I can drag the folder without zipping it first, and it does the zipping on its own. Okay, so we are now in topic 8, and switch back to the file manager. This is the notes that we want, so I can just highlight it and then drag it over to here. So it does the zipping automatically of all the content inside the folder, and then it uploads it too at the same time.
You put last week's up too, then.
Huh?
You put last week's up too, then.
Yeah, it's so easy now. In the past, I thought I had to go through the manual process of creating the zip file and then do everything. It seems like you can do it automatically now. All right.
That status bar is not moving pretty quick though.
So get started with your homework assignment, even though it's due in 12 days. Get started early. So if you have any questions, you can ask it in class.
12 days very quickly turns into half a day.
I have a feeling I'll start around 10.5 days, maybe 11. At least that's how I normally operate.
Yeah.
That's very slow.
I know, right?
That doesn't seem to be working.
The last homework I did today was due.
I emailed you about the assignment that I trimmed.
Oh, okay. So your max?
Yeah.
Okay.
Yeah, as long as I can show it to you. I couldn't come later earlier to the lab today.
Okay.